amplifier. In that, we are going to see about the DC performance and AC performance separately. The first one is DC performance. In DC performance, what are all the things that we are going to see is operational amplifier. What is meant by an operational amplifier? Input resistance of the operational amplifier, output resistance, open loop gain, bias current, offset voltage, common mode rejection ratio, negative feedback amplifier, closed loop gain, and differential amplifier in the DC performance. Whereas in the AC performance, frequency response and transient response, stability compensation, poles and zero cancellation. That is what we are going to see in the second half of the module number 1. Before going into it, we need to know what is meant by an integrated circuit. Integrated circuit, otherwise said to be IC, is a miniature, and it is of low cost electronic circuit. It is a low cost.
Ma'am,
yeah.
You shared the YouTube link, asynchronous sequential circuit. In that, there are 5 steps. Third or fourth step, I can't understand from video.
Okay, I'll explain you once I'm completing this, maybe in tomorrow class. After this class, you tell me where you couldn't understand.
Okay, ma'am.
Huh? Okay.
Okay.
So your next unit is before that we need to go ahead with your integrated circuit. What is mean by an integrated circuit? Integrated circuit is nothing but a miniature or an IC. It is an IC and it is a miniature low-cost electronic circuit consisting of active and passive components that are joined together on a single crystal chip of silicon. Okay, on a single crystal chip of silicon, like that, like this. So in the single silicon chip, you'll be having active as well as passive component, and it's a miniature. It is otherwise said to be an integrated circuit, and it is fabricated on a single. Passive and active components are joined together on a single crystal chip of silicon. And most of the components used in IC are not similar to conventional components in appearance, although they perform similar electrical functions. Okay, right. So now these integrated circuits or ICs are manufactured. This miniature and manufactured in bulk processing or batch processing. Why we are doing miniaturization is it will increase the equipment density and it will increase the system reliability and it will improve the functional performance, and then it increase the operating speeds, reduce the power consumption of the active and the passive component when it is powered with a power supply. Either it is an AC supply or it can be a DC supply. So you may have different types of classification of integrated circuits. Namely, so classification of ICs broadly are classified into 2 types. One is digital IC and another one is linear IC. One is digital IC and another one is linear IC. So these two ICs, two distinctly different IC technology, uses two distinct IC technologies, namely monolithic technology and hybrid technology. Okay, in monolithic integrated circuit, all the circuit components, both active and the passive elements and the interconnections are manufactured into or on the top of a single silicon chip. In monolithic, all the passive components are fabricated on the top of the silicon chip, on the top of the silicon chip. Whereas in the hybrid technology, separate component parts are attached to a ceramic substrate. All the components, separate components, namely active component as well as passive component. Passive component are attached to a ceramic substrate, and then they are interconnected by means of either wire or metallization. So based on this technology, we are going to, they are developing the digital IC or analog IC. So now there are, based on this IC technology, you are having different types of IC technology. One is IC chips based on the chip size and the circuit complexity. Based on the chip size and the circuit complexity, these ICs are classified into small scale integrated circuit, medium scale integrated circuit, large scale integrated circuit, very large scale integrated circuit, ultra large scale integrated circuit, and giant scale integrated circuit. So first one is based on the number of components, available on the IC, component in the sense number of active components in active or passive components available in an IC. This is classified into small scale integration, large scale integration, very large scale integration, and then ultra scale, large scale integration, and then GSI, gain scale integration. Okay, gain scale integration. So the development of the silicon IC technology began in the year 1947. And then till 2000. This in the year 2000, your GSI has come up. So over the years from 1947 to 2000, the chip size have been reduced from around it will always be in mm square. So for the chip areas will range from 16,000 mm square, 1,600 mm square to 1,60,000 mm square. The chip area will range in this. The chip area will vary in this range. So we are not going into deep about the manufacturing process of IC technology. So linear IC is nothing but the characteristics of your linear integrated circuit. Your input and output will be linear. That is said to be your linear integrated IC. And then we are one among the linear IC is 741 IC. One among the linear IC is 741, IC741, integrated circuit IC741. IC741. So it is available in either as an 8-pin or 10-pin or 14-pin IC. It is available as 8-pin IC, 10-pin IC and 14-pin IC. Mostly we will be dealing with 8-pin IC. And this is the pin configuration. You will have a notch at the top. This is the notch in an IC. And the left side you have a dot. Like this. So from that left hand side you will be counting 1, 2, 3, 4, 5, 6, 7, 8 pin number, of which pin number 2 is said to be an inverting input. Pin number 3 is said to be a non-inverting input, and 6 is said to be an output. And the power supply will be given in 4 and 7. Power supply for the chip is given at 4 and 7. The power supply ranges from 5 volt plus or minus 5 volt to plus or minus 22 volts. And the pin number 8, we don't have any connection, and you have an offset null in pin number 1 and pin number 5. So different type of packages are available in the IC. The first one is said to be a DIP package, dual inline package. It is said to be dual inline package, DIP package. We can insert this in the breadboard. who would have inserted this sort of ICs in a breadboard. And this one is TO package. This one is said to be TO package, otherwise said to be metal can package. This is otherwise said to be metal can package. And the third case is said to be the flat package. Okay. This will be used in PCBs. It can be used in PCBs, printed circuit boards. This is a surface mount IC. This is available in flat package. Okay, it is available in a flat package. And who are all the manufacturers that they are producing this 741 are Fairchild, National Semiconductors, Motorola, RCA, Texas, Signetic, Burr Brown. And they will have the Motorola, I mean, each manufacturers will have their codes, okay, will have their own codes, short forms or abbreviations, in any way we can tell. They have, so based on the codes, we can identify who is the manufacturer. Fairchild, usually it will be designated as MUA or MUAF. National Semiconductor, LM, LH, LF, TBA. Motorola, MC, MFC. And RCA, CA, CD. Texas SN and Signetic NBASI or NESC. Burr Brown is BB. So, for example, if it's a national semiconductor 74 IC, representation of national semiconductor 741 is, we'll be representing it as LM741. We'll be representing it as LM741. And you will have different grades of ICs, or different classes of ICs. You have different classes of ICs. Okay. The first one, we have a military grade op-amp. Military grade op-amp, that is 741. This is military grade op-amp. The second one, 741C, that is said to be commercial grade op-amp. Commercial grade op-amp. It varies in the operating temperature. Military grade op-amp operates with the temperature from minus 55 degree to plus 125 degree, whereas 741 operating temperature, it will be, sorry, the screen is freezing. 741 commercial grade IC will range from 0 to 70 degree centigrade. And the next one is 741A, and the fourth one is 741E, and fifth one is 741S, and sixth one is 741SC. Whereas 741A and 741E, these two are the improved version of the military grade 741. It will have better electrical specifications. And 741S, it is military grade op-amp again with the highest slew rate. And 741SC, commercial grade op-amp with higher slew rate. We will see once the course is started, we will see what is mean by slew rate. With higher slew rate. Commercial grade op-amp with higher slew rate. Right. So next is your operational amplifier. What is an ideal operational amplifier? As I said already, it is available in 8-pin, 14-pin and 10-pin IC. And whereas 2 is said to be an inverting input and 3 is said to be, you have 2 input pins, namely 2 and 3. You both are inputs. Second pin is a negative pin and third pin is a positive pin. And you have an output called in the sixth pin. Whatever input I'm giving it here, take for example, if I'm giving an input of 5 volts here in the inverting input, output I'll be having it as a -5, for example. So you'll have, if I'm giving 5, since this is an inverting input, I'll be having -5. And if I'm giving +5 here, I'll be having +5 at the output in the non-inverting. So if I'm giving +5, I'm taking it as -5. That is said to be, you have 180 degree phase shift. You have a 180 degree phase shift between the input and the output. between the negative input and the output. And whereas for the positive input and the output will be in phase because there is no change in the sign. Hence it is said to be the in phase. Okay, right. So before going into detail, let me draw the schematic symbol of op-amp. Schematic symbol of op-amp. Generally, op-amp will be represented by a triangle symbol like this or an arrowhead like this. So you have two input terminals and one output terminal. Pin number 2, pin number 3, pin number 6 if it's an 8-pin DIP. And then this is a negative input terminal. This is a positive input terminal usually. And how will I represent? This will be plus VCC and this will be minus VCC. This is how it will be represented. Mostly they won't represent VCC, it is understood, but for your understanding and drawing the plus VCC and minus VCC, it is available at 4 and 7, pluses at 7. So pluses are pin number 7 and minus is available at pin number 4. Okay. So now let me name, yeah, let me take a different color. So let the input at the positive terminal, this is said to be non-inverting terminal. Why the name non-inverting terminal is, whatever input that I am giving in this terminal, the same output I will be getting. So that is said to be non-inverting terminal. Whereas this is said to be inverting terminal. Okay, right. So now this input is V2. Okay, let me name this as inverting terminal input as V2. And now output will be represented as V0. Let the current, let me take a different color. Let the current flowing through this terminal be I1. I1 is equal to 0. I'll tell you why it is 0. And this is I2. I2 is also equal to 0. Okay. And this differential potential V1 minus V2, it is said to be VD. That is also equal to 0. Okay. So the characteristics, this is ideal op-amp. The characteristics of ideal op-amp that we are going to discuss. Now, what is said to be an ideal op-amp is? So here, if your input, as I said already, you have a phase shift between this negative input and the output, and you don't have a phase shift between 3 and 6 if I'm giving input here. So V1 and V2 are the inputs of the op-amp. Okay, for an ideal op-amp, no current enters through your op-amp because your input impedance of the op-amp, ideal op-amp, one of the characteristic is input impedance or resistance, whatever. Input impedance is infinite in your op-amp. Input impedance and open loop voltage gain of the op-amp, let me represent it as AOL, that is infinite. Number 3 is output impedance is 0. And number 4 is bandwidth of the op-amp is infinity. Number 5 is, yeah, this is the 4 characteristics. Fifth one, what I need to tell you is, you have a 0 offset. You don't, that is, you have a 0 offset. That is V0 equal to 0 when V1 equal to V2 is equal to 0. Okay, you have a 0 offset when V0 equal to 0. That is when V1 and V2 are 0, V0 is also equal to 0. Let me repeat, it is an 8-pin DIP I have drawn. You have two input terminals, inverting terminal and the non-inverting terminal. inverting and the non-inverting terminal, and you have an output terminal. You have an output terminal. So now V1 is the input terminal and V2 is the output. Sorry, V1 and V2 are the input terminals. V0 is the output terminal. Okay, and difference between V1 and V2 is termed as the difference potential VD. Usually that VD will be equal to 0. Usually VD will be equal to 0, meaning there won't be any current flowing through your for an ideal op amp, there won't be any current flowing through your op amp, because your input resistance is infinite. Because your input resistance is infinite and the gain is infinite, open loop voltage gain is infinite, output resistance is 0. Okay, so when I'm telling that input impedance is infinity, when I'm telling that input impedance is infinity, when I'm telling input current is infinite, it means that the op amp does not draw any current. Okay, it won't draw any current at both the input terminals. So when I'm telling that input resistance is infinity, this op amp won't draw any input current, either I1 or I2 inside it. So I1 equal to I2 is equal to 0. Let me go ahead with the next slide. So it means that I1 equal to I2 is equal to 0 when op amp does not draw any current at the input terminal. Why this happens? This is because your input impedance is infinite. This is because your input impedance is infinite. And then what does it mean is, because of the input infinite input impedance, any signal source can drive the op amp. Any source can drive the op amp, and then there won't be any loading in the preceding driver stage. Preceding means before. If I'm connecting any driver before, or any op amp before, or any circuit before this op amp, there won't be any loading in that, because your input impedance is infinite. So case number 2 is the gain is infinite. That is AOL. I'm telling it as infinite. Since the gain is infinite, the voltage between the inverting and the non-inverting terminal, that is the difference potential, will be essentially 0 for finite output voltage. See, since I'm telling AOL is infinity, since I'm telling A1 is infinite, the voltage between the inverting and the non-inverting terminal, okay, in the inverting and the non-inverting terminal will essentially be 0. Meaning V1 minus V2 is equal to 0. V1 minus V2 is equal to 0, which is nothing but, what is V1 minus V2? It is a difference in potential VD. Okay, for finite output potential, this difference in potential will be 0 for a finite output voltage. The third one is the output voltage is independent of the current drawn from the output. Since the third one, what we are telling, that R0 is equal to 0. What does it mean? If R0 is equal to 0, it acts as a short circuit. So your current drawn from the output voltage is independent of the current drawn. Output voltage is independent of the current drawn. Okay, right. The current drawn is independent. The output voltage is independent of the current drawn. So these are basically the 3 important characteristics, and one more is bandwidth is infinite, that we will see later. So now when I'm telling this is the ideal op amp representation is this. But the practical op-amp representation, I'll do it. How will we represent a practical op-amp is? I have an input resistance Ri. The difference in voltage is Vd. Okay. So V2 and V1. The difference in voltage is Vd. And then I have a dependent source AOL into Vd. Dependent voltage source. And I have a resistance called R0. And where this is my output voltage. Okay. Where V0 is nothing but AOL into Vd. Since it's open circuited, this is a Thevenin's equivalent circuit. Okay. This is how it will be represented. Where your you have an voltage controlled voltage source AOL into Vd, and that is the AOL into Vd is an voltage control source, voltage control voltage source. This and all you would have been read in your network theory. Voltage control voltage source, and that is the Thevenin's equivalent as well. Thevenin's voltage source, and R0 is the, when you look at this, this is equivalent to a Thevenin's equivalent. This is an voltage source. This is a Thevenin's resistance. This is the Thevenin's resistance. Okay. So from this circuit, we can write V0 is nothing but AOL into Vd, and we know what is Vd. What is Vd? Vd is nothing but V1 minus V2. Okay, because this is your non-inverting input, this is your inverting input. So V0 can be written as AOL into V1 minus V2. Okay, V1 minus V2. Right. So now the open loop operation of the op-amp. How to analyze the open loop operation of op-amp is, see, either the output of the op-amp, either you will be giving input in the positive terminal or in the negative terminal, or in both in both the terminals. Okay, if you give input in both the terminal, that will act as a differential op-amp. Op-amp is otherwise said to be operational amplifier. It is otherwise said to be operational amplifier. So when for an open loop characteristics, for example, open loop circuit of an op-amp, open loop of circuit, I'll be applying an voltage of V2 and then an voltage of V1. I'll be having an output. This is minus, this is plus, and this is Vd. Okay. So my V0 will be either at the positive saturation, V0 may be at positive V saturation level, output level. If V1 is greater than V2, V1 is given at a positive terminal, as I said. So when I'm giving voltage at the positive terminal, output and the input will be in phase. When I'm giving voltage input at the negative terminal of input, output and input will be out of phase by 180 degree. So this V0 can have any two values, either plus or minus V saturation. When you will get V saturation is if V1 is greater than V2. And when you will be getting minus V saturation, output is when V2 is greater than V1. Okay. So this operational amplifier will act as a switch between your positive V saturation and your negative V saturation. Okay. Right. So your next thing is the feedback of an ideal operational amplifier. So we will be dealing with the negative feedbacks, and how op amp can be used in a variety of ways by providing feedback to the operational amplifier. There won't be any use if you operate an op amp in an open circuit. We need to operate the op amp in the closed circuit. So meaning you will have feedback, negative feedback. So the utility of an op amp can be increased by providing negative feedback. The output in this case is not driven. See, in open loop condition, as I said in the previous slide, in open loop, there is no feedback in this op amp. We are simply giving the input and we are taking the output. In that case, the op amp will behave as a switch, meaning output may vary, switch between positive V saturation and negative V saturation. Only if we give a feedback, negative feedback is preferable. So if we give a feedback from output to input, this saturation won't occur. The output voltage will be within plus or minus V saturation. Okay, within the saturation level. So now the output in this case is not driven into saturation if we give a negative feedback, and the circuit behaves in a linear manner. And we are going to discuss about only linear integrated circuit. So we need to give a feedback, negative feedback. So two important negative feedback circuits that we are going to discuss here. There are two basic connections, feedback connections used. In order to understand the operation of these circuits, we need to make some assumptions. The first assumption is, okay, once the feedback is given, we need to use the following assumptions for analyzing the op amp. What all the assumptions are? The first one is the current drawn by either of the input terminals. One current we know, I1, another current is I2. So the current drawn by either of the input terminals is negligible. Okay. For ideal op amp only, these two are 0. And the next one, the difference input voltage, VD, is essentially 0. These two are the assumptions we need to make while analyzing an op amp with a feedback circuit. So the first thing, let us read about an inverting amplifier. Okay, inverting amplifier. The first thing we need to see is about the inverting amplifier. So let me draw the circuit diagram of the inverting amplifier. You have an output V0, and then I have R1. This is, let it be input voltage. Input current is 0. And the second terminal, this is inverting terminal, because we are going to read about inverting amplifier only. And positive terminal will be grounded. So this current is 0. This one. Yeah. This current is 0. Let me name this current as I1 since it flows through R1, and I have a feedback resistor, as I said, that is represented as RF. Okay, that is connected between output and the input. As I said, what is the first assumption? Input drawn by the op-amp is negligible, meaning op-amp should not draw any current from the source. So whatever input input current that is coming here, I1, that will flow through RF and it will go out like this, according to our assumption. There won't be any current inside. There won't be any current flowing inside the op-amp. So I is equal to 0. Okay. And then what we know already, difference voltage VD is equal to V1 minus V2. Okay. So this is V1 and this potential is V2. Am I right? This potential is V2, V1 and V2. If V1 is 0, and this is also 0 because this is virtual ground. The difference in potential has to be 0. So V1, this is virtual ground, this is virtual ground. Okay. So VD is essentially 0. That is our second assumption. VD is essentially 0. So with that in mind, so we know this is the input applied through R1. Input applied to the op-amp through R1. So how can we write this I1? I1 is nothing but, I'll write it here. Please wait. So I1 is nothing but Vi divided by R1. And since no current drawn by the op-amp, all the current flowing through R1 has to flow through RF. That I already said to you. So V0 is equal to minus of I1 into RF. Okay. V0 is equal to minus of I1 into RF. So how can I write? I can substitute. Let me write this as equation number 1. This is equation number 2. Use 1 and 2. So I'll be taking it as V0 is equal to minus of Vi by R1 into RF, and V0 by Vi is equal to minus of RF divided by R1. This is said to be the gain or the closed loop gain, ACL, closed loop gain of inverting amplifier. Closed loop gain of inverting amplifier. Okay. We can even write what is that? KCL equations here. So V2 minus Vi equal to 0. V2 minus Va by R1 plus V2 minus V0 by RF equal to 0. Like that we can write, and then we can arrive at this solution too. Okay. We'll do that in the problems. Okay. So if you see here, what is the closed loop line before this again, V0 is equal to, V0 is nothing but minus of Vi into RF by Ri. I have a negative sign for the input output V0. It means that there is a phase shift between input and the output. That phase shift is exactly 180 degree. Okay. So if these resistances are replaced by the impedances, the same equations can be represented by, ACL is equal to V0 by Vn, which is equal to which is equal to minus of ZF divided by Zi. Okay. ZF divided by Zi. Okay, let us solve one problem. With that, I'll complete today's session. This is the problem diagram. Minus plus. I have an input of 5K, R1, I1, VI. I will have a feedback resistance of 10K. I1 also, the same I1 will be flowing. This is the feedback resistor RF. I0. I have a load resistance of 10K. Load current will be flowing upward. This is my V0. Whereas this is grounded. Okay. Right. Please note down the problem. For the circuit shown in the figure, calculate. For the circuit shown in the figure, calculate I1, V0, IL, total current, and then what's up? So you have four combinations. You need to find four combinations: I1, V0, IL, and the total current. How will you find I1? Any answers? Do you hear me? Do you hear me?
Yes, ma'am.
How will you find I1? Tell me the formula for I1. What I have written here for I1? What is I1?
VI
by
R1.
R1. In this problem, what is your VI given? Any VI is given? VI, take it as 1 volt. VI, take it as 1 volt. So we know that I1 is nothing but VI by R1 for subdivision A. First problem. Subdivision B, it is asked for V0. How will you find V0? What is the formula for V0? What is the formula for V0? What is V0? Answer me. Minus of
I1 into RF.
VI into RF by R1. Right? Minus of VI into RF by R1. And what about the third one? Subdivision C, it is asked for load current IL. How will you find IL? How will you find IL? Where is your IL? It is in the this node, this V0. How will you find IL? How will you find IL? Look at the diagram and tell me, how will you find IL? Any answers? It is V0 by RL. What is RL? 10K. This is RL. Finally, you need to find the total current. D. Subdivision D. Total current is nothing but I0. What is I0? It is I1 plus IL. I1 plus IL is the total current. Any doubts here? Do you have any doubt here today?
No, ma'am.
I am stopping the recording and come back again.